Welcome to Night Cosmos Sleep, where we step away from the familiar sounds around us and listen instead to the signals moving through the darkness of the universe. Some cosmic events unfold over millions of years, but AT2024 WPP needed only a few days to flare with extraordinary intensity, reaching a brightness equal to hundreds of billions of suns before rapidly fading, as though a door had opened in the dark and closed again before we had time to see what lay beyond it. What made the event even stranger was that the source did not cool in the way astronomers expected. Signals from the deepest region disappeared and then returned, while the matter surrounding the center continued to move long after the brightest phase had passed. Perhaps a star wandered too close to a black hole and was pulled apart from its original form. Or perhaps the story began with a binary system quietly orbiting for a very long time until the distance between its two members became impossible to recover from. But to understand what may truly have happened, we need to return to the beginning, to the moment a distant point of light appeared in the sky, opening one of the strangest mysteries the universe has ever sent toward Earth. To trace the mystery of AT2024 WAP, we need to return to the moment when its first signal was recognized on Earth. It did not arrive as a dramatic image of a star being torn apart, or as the unmistakable darkness of a black hole, but as a very small change between two observations. On a screen, two images of the same region of sky were placed side by side, nearly identical, down to every point of light. Yet in the later image, near the edge of a faint galaxy, a new speck had appeared where nothing had been visible before. That tiny sign marked the beginning of an effort to follow an event that had taken place more than 1 billion years ago. No sound of an explosion reached Earth. The space between celestial objects is almost empty, so sound cannot cross such a distance. Nor did a vast fireball appear clearly enough for anyone to see with the unaided eye. From this far away, an event powerful enough to disturb an entire star system is reduced to only a few faint pixels. Its first sign was so subtle that, without cameras continuously watching the sky, the point of light might have appeared and vanished without anyone ever noticing. The images came from the Zwicky Transient Facility, an observing program that uses a telescope at Palomar Observatory in California. Its task is not to stare for long periods at a single star. Instead, the telescope repeatedly photographs wide regions of the sky, night after night, building a sequence of images of the same familiar places. Most points of light remain fixed. Distant stars show almost no change during the short interval between one image and the next. Galaxies also preserve their faint, steady appearance. It is this repetition that makes small changes easier to detect. A new point of light, a star that suddenly grows brighter, or an object moving across the background can all be flagged by computers for closer examination. The search begins with difference. A new image is compared with images taken before it. The parts that remain the same are almost entirely removed, leaving behind only what has changed. Most of these signals do not lead to a distant cosmic event. Sometimes the source is simply an asteroid passing through the telescope's field of view. Sometimes a high-energy particle strikes the camera and creates a false point of light. Even a small recording error can leave behind a mark that resembles a newly appeared star. So before astronomers can say that the universe has produced something unusual, they must first rule out more familiar explanations. They check whether the point of light moves between exposures. They review its shape, its position, and earlier images of the same region. If the signal remains in the same place, continues to brighten, and lies within a distant galaxy, the possibility that it is a real event begins to become much clearer. The new point of light was given the name AT2024 WPP. It sounds cold and impersonal, more like an entry in a database than the name of a major cosmic event. The first part identifies it as an astronomical phenomenon that appears only for a limited time. The remaining characters distinguish it from the many other transient sources discovered during the same year. The name says nothing about its shape, reveals nothing about its origin, and offers no clue about what is happening inside it. Later, it was given a more memorable nickname, Whippet. The name comes from a breed of dog known for its slender body and rapid acceleration. The nickname was not inspired by the shape of the source, because at this distance no telescope could resolve its true form. It came from the way the event changed. Whippet did not seem to spend much time slowly entering view. It appeared, and then brightened quickly, as though something had suddenly been released on the far side of the universe. At that point, astronomers still did not know what they were seeing. A star may have reached the end of its life. A binary system may have been passing through a violent transformation. Matter may have been falling toward a dark object at the center. Or Whippet may have belonged to a class of events so rare that no existing explanation fit it completely. At first, all they had was the position of a point of light and the way it changed from one image to the next. That position lay within a galaxy about 1.1 billion light-years from Earth. The number is so large that it is difficult to compare with any distance familiar from daily life. Even light, the fastest thing we know, requires more than 1 billion years to travel from that galaxy to telescopes on Earth. When we say that an object is 1 light-year away, it does not mean that light takes a year to travel around it. It means the distance between two places is so great that light needs an entire year to cross it. For Whippet, that journey lasted more than 1 billion years. The event astronomers discovered in 2024, then, did not truly happen in 2024. By the time the point of light appeared on a screen at Palomar, everything in that distant galaxy had ended long ago. The source may already have faded. Streams of matter may have traveled far from where they began. The star that once existed there may no longer have retained its original form. The black hole, if a black hole was truly part of the system, may already have returned to an almost invisible state. Only the light was still on its way. For more than 1 billion years, that signal crossed the space between galaxies. It moved through regions containing almost no matter, passed through faint clouds of gas, and continued traveling as the universe itself kept changing. No one guided its path. No destination had been chosen in advance. The light simply continued onward until a very small portion of it reached the mirror of a telescope on Earth. To understand that delay more clearly, we can begin with places much closer to us. Light from the moon takes a little more than a second to reach our eyes. When we look at its pale surface, we are seeing the moon as it existed more than a second ago. The sun is farther away. Light from its surface takes about 8 minutes to reach Earth. If a change were to happen on the sun at this very moment, we would still have to wait roughly 8 minutes before receiving the first sign of it. The image of the sun in our sky does not belong entirely to the present. It is an image that left the sun several minutes earlier. For other stars, the delay may last years, centuries, or thousands of years. For Whippet, it stretched beyond 1 billion years. To look toward the place where it appeared is also to look back through a very deep part of cosmic history. When Whippet's light began its journey, Earth already existed, but the world on this planet was very different. There were no cities, no telescopes, and no human beings to ask questions about the points of light in the sky. Life was still moving through the long stages of evolution. Meanwhile, the light from that distant event continued silently across space. Countless generations of living things appeared and disappeared. Continents shifted. Climates changed. New species emerged. Only after an almost unimaginable span of time did humans begin to look upward, create the first tools for tracking the stars, and eventually build systems sensitive enough to detect a tiny point of light near the edge of a distant galaxy. Astronomers did not witness Whippet in the way someone nearby might watch an explosion. What they received was a message that had traveled for more than 1 billion years. Every photon that reached the camera belonged to an event that had ended before human history began. That distance also made the source difficult to understand. No spacecraft could be sent there. No one could directly watch a star being stretched apart or matter spiraling around a black hole. Even the most powerful telescopes could collect only the light from a small region that could not be resolved into separate objects. Everything about Whippet had to be reconstructed from its signal: how quickly the source brightened, what color it was, how that color changed when the X-rays appeared, whether the radio waves arrived early or late. Subtle features in the light could reveal what kinds of matter were present and how they were moving. Each piece of information was like a small fragment of a much larger picture. No single fragment could tell the entire story. Only when they were placed together in the correct order did an image of the event begin to emerge. During the earliest observations, the clearest fact was that Whippet had not stopped brightening when it was discovered. The source continued to grow stronger. Each new image showed the small point near the edge of the galaxy becoming more prominent. The change happened so quickly that astronomers realized they had only a narrow window in which to observe it. If Whippet reached its peak and faded within a few days, waiting too long could allow the most important stages to disappear from the data. Anything not recorded at that moment could never be recovered. The light that had already passed Earth would continue onward into space, carrying information that humanity would never have a second chance to collect. Alerts about the new source were sent out. Other observing teams began turning their instruments toward the same location. Some telescopes tracked the visible light that human eyes can see. Others searched for ultraviolet radiation, which could reveal higher temperatures. Space observatories checked for X-rays, while radio telescopes listened for signals from matter moving farther outward. They were not all observing the same thing. Each kind of telescope was looking into a different layer of the event. Visible light might come from a broad outer envelope of gas. X-rays could originate closer to the deeper source of energy. Radio waves sometimes become clear only after material has traveled outward and collided with the surrounding environment. At that stage, no one knew whether these signals would tell a single, unified story or lead in completely different directions. The only certainty was that the point of light was changing too quickly to ignore. In many astronomical phenomena, time is measured in thousands or millions of years. A star can remain nearly stable for longer than the entire span of human history. A galaxy changes so slowly that even many generations of telescopes may struggle to detect any clear difference. Whippet was moving to a different rhythm. The event did not require centuries of observation. In only a few nights, the tiny point of light changed enough to draw the attention of observatories both on Earth and in space. The source seemed to be moving faster than the people watching it could respond. Each time new data arrived, the questions became more urgent. How long would it continue to brighten? How luminous would it become at its peak? Would it behave like an exploding star? Or would it follow a path that had never before been observed clearly? Its distance of more than 1 billion light-years made Whippet a story from the past. Yet the speed of its transformation turned that story into a race unfolding in the present. The light had taken more than 1 billion years to reach Earth, but astronomers had only a few days to capture its most important phase. No one could slow the event down. No telescope could ask the source to repeat what had just happened. All humanity could do was observe, record, and wait to see where the light curve would lead. Night after night, the small point near the edge of the galaxy continued to flare. It did not brighten gradually over many weeks, like a flame slowly growing larger. Within only a few days, Whippet reached a level of brightness that made familiar explanations begin to seem insufficient. The signal had taken more than 1 billion years to reach Earth. But once it arrived, it needed only a few days to become one of the most intense sources of light ever recorded. Whippet's light had traveled for more than 1 billion years before reaching Earth. Yet once it touched the observing instruments at Palomar, it needed only a few days to transform from a faint point into the focus of an entire network of telescopes. After its initial discovery, the source did not remain at a brightness just strong enough to be noticed. Each new image showed it standing out more clearly against the sky, as though an invisible door were opening wider and revealing more and more energy from within. Only a few hours, or perhaps a single night, separated one observation from the next. Yet even within that brief interval, Whippet could change noticeably. Astronomers understood that the most important phase of the event was passing before their eyes, and that any gap in the data could become a missing piece of the story that could never be recovered. From the sequence of images, the source's evolution gradually took the shape of a clear path. At first, Whippet rose only slightly above the faint glow of its host galaxy. Then its brightness increased so quickly that the light curve climbed almost vertically. There was no period lasting several weeks in which observers could prepare, and no slow rise to warn that the peak was approaching. Only about 3 to 4 days after the first signal, the source had already reached its greatest intensity. In astronomy, 3 days is almost no time at all. A star may spend millions of years passing through the final stages of its life. Yet Whippet's brightest phase unfolded in less than a single work week on Earth. That pace turned the observations into a strange kind of race. The event itself had ended long ago in that distant galaxy, while on Earth, humanity was merely receiving, layer by layer, the light that had left it more than 1 billion years earlier. The stream of signals passed our planet only once, before continuing onward into space. Whippet could not be asked to repeat its rise. Time could not be reversed to capture another image on a night that had been missed. Observatories could only respond as quickly as possible, rearranging schedules and turning their instruments toward the source before its state changed again. Its speed was not the only thing that made Whippet unusual. When the measurements were combined, its peak brightness was estimated to be equivalent to roughly 400 to 500 billion suns shining at the same time. This was not the mass of the black hole, nor was it the number of stars destroyed in the event. The figure simply offers a way to imagine how much light the source produced during its most intense phase. Even when understood correctly, however, the scale remains difficult to compare with anything familiar. The sun is only an ordinary star, yet its light is enough to illuminate the entire daytime sky. Whippet lay more than 1 billion light-years away, and still, the small portion of its light that survived that immense journey remained bright enough to appear in data collected from Earth. A source this luminous does not necessarily have to be enormous. In fact, the speed of the rise suggested that most of the energy was probably being released with one packed region. A structure spread across too much space would struggle to change as a whole in only a few days, because light from different parts of the source would need time to cross the entire region. Whippet changed too quickly for that. Whatever machine lay behind the light had to be both extraordinarily powerful and far smaller than the galaxy that contained it. A wider envelope of gas may have surrounded the central engine, but the region producing most of the energy was likely buried deep inside. At the moment Whippet reached its peak, astronomers still did not know exactly what mechanism had caused it to flare. A massive star may have entered the final moment of its life. Matter may have been falling rapidly toward an extremely dense object hidden at the center. Another possibility was that a deep central source was illuminating the surrounding gas, causing a much larger region to glow. During the first few days, these scenarios could produce very similar appearances, especially when the entire event remained unresolved as a single point of light. The light revealed the result, while the process that created it remained concealed behind layers of matter. Its speed, color, and luminosity placed Whippet within a rare class of phenomena known as luminous fast blue optical transients, usually shortened to LF-bots. The name sounds complicated, but its meaning is fairly simple. These are extremely bright sources that appear blue and change rapidly in the optical light recorded by telescopes. Being placed in this category did not mean that Whippet's origin had been explained. The classification only showed that it shared certain features with events observed before. The story inside each source could still be very different. Whippet pushed those characteristics to even greater extremes. It was brighter than many previously known events of the same general type, and reached its peak in an unusually short time. It may therefore have been a rare and powerful version of a familiar phenomenon, or it may have represented an entirely different path leading to a similar appearance. In the universe, two events do not necessarily share the same origin simply because both brighten quickly and appear blue. A collapsing star, a black hole drawing in matter, or a binary system entering its final stage can all produce signals that look nearly identical during the first few days. The true differences often emerge only after the light begins to fade and the deeper layers gradually come into view. Whippet remained near its maximum brightness for only a short time. The point of light did not linger at the peak for weeks, but quickly entered a fading phase. Its light curve formed a narrow shape, rising steeply and turning downward almost immediately, like a sharp mountain peak emerging from a relatively flat stretch of data. In less than a week, the brightest part of the event had nearly passed. A source that had briefly shone with the power of hundreds of billions of suns began to weaken before many telescopes had even completed their first rounds of observation. Ordinarily, after a stellar explosion reaches maximum brightness, its material expands outward. As the ejecta spread, their density falls and their temperature decreases over time. The color therefore tends to change, moving from hotter shades of blue or white toward redder tones as the source cools. Whippet followed only part of that pattern. Its total brightness declined rapidly, but its blue color did not disappear at the same rate. The source was fading while still showing signs of very high temperatures, like a flame growing smaller, while what remained continued to burn intensely hot. This separation between brightness and temperature suggested a different way of understanding the event. The visible emitting region may have been shrinking while the remaining area stayed hot. The surrounding gas may also have become thinner, reducing the effective radiating surface even though the central energy source had not weakened by very much. Some of the energy may have shifted into forms of light invisible to the human eye. These possibilities could not yet be distinguished, but they all pointed toward the same conclusion. Whippet's decline was not simply the cooling of an expanding fireball. A more fitting picture is a system made of many layers. On the outside, the region of gas producing visible light is changing rapidly. Deeper within lies a hotter region that may generate ultraviolet light or X-rays. Farther outward, material driven away from the center may take weeks to collide with older gas and begin producing radio waves. These signals do not appear at the same time because they come from different regions and reveal different parts of the same event. Observing Whippet in visible light shows only the first layer of the story. In the days after the peak, observatories continued to record each stage of the source's decline. Optical telescopes followed the most easily detected light. Instruments sensitive to ultraviolet radiation searched for signs of high temperatures. X-ray observatories looked deeper, toward the region where a small but intense source of energy might still be active. The data were no longer being collected simply to confirm that Whippet was real. The question had shifted to the nature of the engine behind it. What could produce such an extraordinarily powerful source of light within only a few days, then allow it to fade without cooling as expected? An ordinary star would struggle to release that much energy without leaving clearer signs behind. A single explosion would also have difficulty maintaining such high temperatures long after the light had begun to decline. The possibility of a continuing energy source therefore drew increasing attention. Matter might still have been falling toward the central region, where it continued to be compressed and heated. Energy from within could have illuminated the wider envelope of gas, keeping it blue even as its overall brightness decreased. The moment Whippet reached its peak answered one question. This was not a faint point of light that had appeared by chance in the data. It was one of the most powerful sources of its kind ever observed. Yet it was during the fading phase that astronomers began to realize that its immense brightness might not have been the strangest part. An ordinary fireball would gradually change color as it cooled. Whippet remained blue, as though the engine behind its outer glow were still feeding energy into the system. From that point on, the observations were no longer simply following a source as it faded away. Astronomers began looking deeper into the signals hidden beneath the visible light, searching for the regions that remained hot, and for whatever continued to operate after the brief peak had passed. Whippet had begun to fade, but its blue color remained. Beneath that weakening layer of light, a source of heat with no clearly defined shape still seemed unwilling to fall silent. Whippet had begun to fade, but its blue color remained. In the newer images, the source was no longer as brilliant as it had been at its peak. Yet it was not gradually shifting toward red in the way astronomers would normally expect from cooling material. The brightest phase had passed, while signs of extreme heat were still present, as though somewhere behind the weakening envelope of gas, a heat source of uncertain form was continuing to operate. The color of a light source can reveal a great deal about its temperature. A metal bar placed in a furnace will first begin to glow a deep red. As its temperature rises, it becomes brighter red, then yellow, white, and eventually takes on a more distinctly blue appearance. Stars in the sky show similar differences. Red stars are generally cooler, while blue stars emit light from layers of gas that are far hotter. Whippet's blue color was therefore more than an unusual visual feature. It showed that the emitting region was still holding an immense amount of heat even after the total brightness had begun to decline. Near the time of maximum light, the temperature of the emitting region was estimated to exceed 30,000 degrees. For many weeks afterward, it remained near 20,000 degrees or higher. There is little need to compare such values with a furnace or flame on Earth, because everything familiar becomes far too small beside an environment like this. It is enough to imagine matter around Whippet so hot that much of its radiation shifted toward blue and ultraviolet light, regions of the spectrum usually associated with extremely high temperatures. What stood out was that the brightness and temperature did not decline at the same rate. Whippet weakened fairly quickly after reaching its peak, yet its temperature fell much more slowly. A simple object that is gradually cooling would normally become both dimmer and redder over time. Here, the source was fading while remaining blue. That appearance suggested that the entire system was not behaving like a single fireball expanding and slowly going dark. We might imagine a bed of burning coals. When the red-hot area spreads widely, it fills the room with more light. Later, the burning region becomes smaller, reducing the total brightness, while the coals that remain continue to hold an extremely high temperature. Whippet may have been changing in a similar way. The region producing most of the visible light was gradually shrinking, while the deeper region remained hot. A broad envelope of gas that had once been strongly illuminated was beginning to thin, even though the energy source at its center had not truly shut down. Another image may also help explain this change. Imagine an intensely hot lamp placed behind a broad curtain. When the entire curtain is illuminated, the room appears bright. Later, the curtain contracts or becomes more transparent, reducing the area that gives off light. The room grows darker, but the lamp behind it remains hot. In Whippet, the visible light may have come from a wide region of gas surrounding the true energy source. As that gas changed, the total brightness changed with it, even while the temperature near the center remained high. Astronomers could not directly see the individual layers of the event. All they received was the tiny amount of light that reached their telescopes after traveling for more than 1 billion years. From its brightness, color, and evolution over time, they tried to reconstruct the structure behind it. The measurements did not produce a clear image of matter surrounding a black hole. They only suggested that Whippet contained several distinct regions, each contributing its own part to the light we observed. The outer layer may have been broad and bright invisible light. A deeper region was hotter, producing strong ultraviolet radiation. Closer to the center, matter may have been moving at extremely high speeds, becoming compressed and generating more powerful signals that human eyes cannot see. As each layer changed, Whippet changed with it. A decline in visible light did not mean that all activity inside had ended. The blue color that persisted for many weeks became one of the most important clues. It suggested that the event had not simply received an initial burst of energy and then allowed all of its material to cool on its own. Some process appeared to be continuing to feed heat into the system. Matter may still have been falling toward the central region, or energy from deeper within may have been shining outward continuously, keeping the surrounding gas at a high temperature. The data did not yet allow astronomers to choose between these explanations, but the picture of a simple explosion was becoming increasingly difficult to reconcile with everything they were seeing. To investigate Whippet's composition, astronomers did more than measure its overall color. They also separated its light into many smaller parts. White light may appear uniform, but it actually contains many different colors. When passed through a specialized instrument, it spreads into a band much like a rainbow. Within that band, different elements can leave their own distinctive marks, like small traces of ink appearing at familiar positions. Hydrogen leaves the signature of hydrogen. Helium leaves the signature of helium. Heavier elements also have their own ways of interacting with light. Through these traces, a source millions or billions of light years away can reveal something about the matter surrounding it. Astronomers do not need to collect a sample of gas from Whippet. They only need to read the information carried by its light. Yet the earliest observations of Whippet revealed a spectrum that was almost completely smooth. The familiar signatures of hydrogen, helium, and other elements did not appear clearly. Instead of a page covered in writing, astronomers were given a surface that was extremely bright but nearly blank. The source remained powerful. Its blue color was unmistakable, yet it carried less information about its material than expected. That absence did not mean that there was no hydrogen or helium around Whippet. It only showed that the matter was not producing its signatures in the familiar way. The extreme temperature may have altered the state of the gas. Under such intense radiation, atoms can no longer preserve their ordinary structures. Their charged components are stripped away, causing the usual signatures to weaken or disappear from the spectrum. There is no need to explore the structure of the atom in detail to picture this. We might think of a piece of music being played at overwhelming volume. The melody is still there, but the sound is so intense that the finer details become lost in the echo. Around Whippet, the central energy source may have been powerful enough to drive the gas into such an extremely hot state that the writing of individual elements became difficult to see on the page of light. Another possibility involved the thickness of the surrounding material. Energy from the central region may have been absorbed and released again many times before finally escaping. With each repetition, the original signatures became less distinct, like an image viewed through several layers of frosted glass. What eventually reached Earth would no longer carry the information from the place where the energy was first produced in its original form. It had passed through a broad region of gas, changing and blending before leaving the system. The simplicity of the spectrum, therefore, became an important clue of its own. A source that shines intensely while revealing almost no clear composition often suggests that the surrounding environment is in an extreme state. The matter has not vanished. It has simply been heated and illuminated so powerfully that its familiar traces have become obscured. During the first few days, this made Whippet's origin even more difficult to determine. A stellar explosion usually leaves behind many chemical signatures that help identify the layers of material thrown outward. From the positions and shapes of these features in the spectrum, astronomers can determine whether a star still contained a great deal of hydrogen or had already lost its outer envelope, how quickly the material was moving, and which elements had recently been released into space. Whippet offered almost none of those clear directions. Its light was bright, hot, and smooth. The answers seemed to be hidden beneath the event's overwhelming energy. Observers knew that a substantial amount of matter was glowing, but they could not yet see clearly what it was made of or how it was arranged. The lack of distinct signatures did not make Whippet simpler. Instead, it increased the number of possibilities. A massive star may have lost most of its outer gas before the event occurred. The material may have been heated too intensely to produce the familiar features. A thick envelope around the center may have been concealing the deeper region. Each possibility explained one part of the observations, but none was yet sufficient to build the complete picture. Meanwhile, the temperature remained high. The light declined day by day, while the blue color changed only slowly. The longer astronomers watched, the harder it became to regard Whippet as an explosion that had completed its work in the opening moment. The energy source appeared to be receiving a continued supply. An engine buried deep within the system was still keeping the material hot long after the brightest flare had passed. A single explosion is like an initial push. Energy is released, matter rushes outward, and then gradually loses heat. With no continuing supply, everything simply keeps moving under its own momentum. Whippet, however, looked more like a system that was still being fueled. Matter may have continued falling toward the center, with each newly arriving layer releasing more energy. That process could last longer than the original flare, and keep the surrounding gas hot for weeks. The possibility of an exploding star had not been ruled out completely. The death of a star can leave behind a compact object at the center, which may then continue supplying energy to the material around it. But Whippet may also have begun in a system that already contained a black hole. A star could have passed too close, lost part of its matter, and sent streams of gas falling toward the center. Both paths could produce an energy source that remained active long after the first burst of light. From more than 1 billion light-years away, there was no way to see the difference between these scenarios directly. There was no image of a star being stretched apart, no clear picture of a black hole or the matter spiraling around it. Astronomers had only the persistent blue color, the high temperature, the fading light, and an almost featureless spectrum to guide them. No single clue was strong enough to close the mystery. Yet, when placed together, they began to point in the same general direction. Whippet was not simply a sphere of hot gas slowly fading away. Inside it, there may have been a smaller, more concentrated energy source that remained active longer than the outer glow. That source had not yet revealed itself clearly in visible light. The blue color only showed that it was still supplying heat. The smooth spectrum suggested that the surrounding gas was either too hot or too thick to expose the structure within. To look deeper, astronomers needed a different kind of signal light, produced in far hotter regions, where matter moves and collides close to the central engine. That signal had already appeared during the first few days, but its behavior was even more difficult to understand than the blue light. It grew stronger, weakened, and then returned weeks later, like a lamp that was sometimes hidden and sometimes revealed through gaps in a surrounding layer of gas. After following Whippet's lingering blue glow, telescopes began tracing its X-rays. They revealed that the deepest region of the event was far hotter and more violent than the outer layer of visible light. After following Whippet's lingering blue glow, telescopes began tracing a different kind of light. It did not appear in the part of the sky visible to human eyes, nor did it carry familiar colors such as red, yellow, or blue. This signal came from far hotter regions, where matter was moving violently near the center of the event. It was X-ray radiation, and from the earliest days, Whippet produced it strongly enough to reveal a deeper region of activity behind the glowing outer gas. The visible light had mainly told the story of the broad envelope of material surrounding the event. This gas absorbed energy from within, heated up, and then radiated in blue and ultraviolet light. X-rays brought observers closer to the central engine. They often arise where matter is strongly compressed, collides at high speed, or falls deep into the gravitational field of an extremely dense object. Whippet therefore no longer appeared to be merely a cloud of gas glowing in space. Hidden beneath the blue light seemed to be a smaller, hotter energy source, operating according to its own rhythm. During the earliest observations, the X-ray signal appeared quite clearly. This was consistent with what the blue color had already suggested. The event had not ended when it reached maximum brightness. A region buried deep inside was still releasing energy, even as the more easily visible light had begun to weaken. From more than 1 billion light-years away, telescopes could not resolve the true shape of this region. They could only measure the amount of X-ray radiation reaching Earth and track how the signal changed from one day to the next. If visible light resembles the bright outer portion of a flame, X-rays are closer to the heat buried deep within its core. Both signals may come from the same event, but they do not necessarily change in the same way. The outer gas can fade as it expands, while matter near the center continues to fall inward, becoming compressed and heated. At other times, the inner region may remain intensely bright, but become hidden behind thick gas, reducing the amount of X-ray radiation able to escape toward Earth. Whippet began to display exactly this kind of complex behavior. After an initially strong phase, the X-ray signal gradually weakened. During some observations, it became much harder to detect than before. The decline did not follow a simple path, nor did it occur in step with the blue light outside. While the optical emission continued to be tracked fairly steadily, the signal from deep within seemed to retreat behind the surrounding material. At first, it might have appeared that the central energy source was slowly shutting down. Its supply of matter may have been running out, or the rate of infalling material may have slowed after the initial flare. Yet a weakening X-ray source does not necessarily mean that the engine behind it has stopped operating. Sometimes the greatest change occurs not within the source itself, but along the path the light must travel. Imagine a lamp placed behind several thin curtains. When the layers of fabric overlap, even a powerful light becomes faint. The lamp continues to burn, but someone standing outside sees only a small fraction of it. If the curtains shift, open a gap, or become more transparent, the light can shine through again without the lamp itself growing any brighter. Around Whippet, the expanding gas, changing from day to day, may have played a similar role. The material that glowed during the first few days did not remain still. It continued spreading outward, forming layers of different densities. Denser regions concealed the center more effectively, while thinner regions allowed X-rays to escape more easily. This motion did not have to occur evenly in every direction, so the amount of radiation reaching Earth could rise or fall depending on the structures through which it had to pass. Another possibility involved the flow of matter near the center itself. The rate at which gas fell inward may have changed over time. After the first surge, a temporary gap may have formed before a new stream of material returned. The X-ray region would then weaken and later brighten again. Streams of gas that had once belonged to the star would not necessarily reach the center at the same time. They could follow different orbits, take different lengths of time to return, and supply new energy in separate waves. Astronomers did not yet need to choose between these possibilities. What mattered more was what happened next. More than a month later, around the 50th day after Whippet was discovered, the X-rays suddenly brightened again. The signal not only became easier to detect, but rose to a new peak, showing that the central region had never truly fallen silent after the first flare. That return changed the way the entire event was understood. Whippet no longer resembled an explosion that released its energy in a single moment and then allowed everything to fade. A long-lived source of activity was present at the center. It may have been hidden, varied in strength, or received new material in separate episodes, but it continued to create conditions hot enough to produce X-rays many weeks after the visible light had begun to decline sharply. 50 days is not long compared with the lifetime of a star, but it is remarkably long for an event that reached maximum brightness in only a few days. Whippet's fastest and brightest phase had ended long before. Optical images no longer showed the source at anything close to its original intensity. Yet deep inside, energy was still being released, like an underground stream continuing to flow after the rain above had ended. The X-rays were not completely steady either. They varied over shorter periods, suggesting that the emitting region was relatively compact. A region spread across too much space would struggle to change as a whole over a short interval. A smaller source can brighten or fade more quickly because its different parts can respond to one another in less time. This offered another clue that the main engine lay deep within the system, rather than being distributed throughout the broad envelope of glowing gas. The regions that produce X-rays in the universe are often associated with matter moving around extremely compact objects. When large amounts of gas are drawn into a powerful gravitational field, they accelerate, collide, and heat up until they begin emitting this high-energy form of light. A neutron star can create such an environment. A black hole can do the same through the material spiraling around it. In Whippet's case, the immense amount of energy, together with signals appearing across many wavelengths, made a black hole one of the most closely considered explanations. Even so, no telescope captured an image of a black hole at the center of the event. At a distance of more than 1 billion light-years, the entire system appeared only as a tiny point. What astronomers observed was the light from the matter surrounding it, not the dark object itself. The black hole left only indirect traces in the way the gas moved, heated up, and released energy. It is much like seeing leaves swirling in circles across a yard without being able to see the wind. The wind has no clearly visible shape, but the motion of the leaves reveals that it is there. In Whippet, the streams of hot gas played the role of those leaves. They brightened, changed, and emitted X-rays under the influence of an extremely powerful gravitational force. From that behavior, astronomers inferred the presence of the hidden object at the center. A completely isolated black hole produces almost no light. It can remain in darkness for an immense span of time without revealing its location. Only when matter approaches does the system become easier to detect. The infalling gas does not disappear immediately. Before reaching the deepest region, it moves around the black hole, collides with other streams of gas, and releases an enormous amount of energy. For that reason, the phrase "a black hole flaring" is only a convenient shorthand. The dark region at the center does not shine like a star. What becomes luminous is the matter trapped around it, like a ring of fire surrounding a place of complete darkness. Whippet may have grown so brilliant not because the black hole itself changed, but because an immense amount of material was suddenly delivered into its vicinity. The next question, then, was no longer only how the X-rays were produced. More importantly, where had all that material come from? A black hole cannot create the gas spiraling around it. A star, or some reservoir of matter, must have entered its gravitational reach. Whippet's energy suggested that the amount involved was far from small, and that the supply process may have unfolded much more rapidly than in ordinary black hole systems. The return of the X-rays around day 50 also suggested that the material did not reach the center all at once. Different streams of gas may have returned one after another, like waves arriving at the shore in separate sets. The first wave produced the intense light seen during the opening days. The source then weakened before another stream moved inward and caused the central region to brighten again. The outer gas continued to change during the same period. As it expanded, its density decreased, and regions that had once been hidden began to emerge. X-rays from the center may then have passed through more easily, making the source appear brighter again, even without a dramatic increase in the true energy being produced inside. Both processes, the changing power of the source and the changing layer that obscured it, may have occurred together, creating a complex X-ray light curve that no single simple explanation could fully describe. It was precisely this complexity that made Whippet so important. A source that rises and falls along a smooth path may be explained by a single process. Whippet behaved differently in each kind of light. Its optical emission peaked early and faded quickly. The blue color remained. The X-rays weakened and then returned. These clues suggested that several regions were active at the same time, each with its own size, temperature, and rhythm of change. Rather than a simple fireball, Whippet began to appear as a dynamic system. At the center was a compact object, most likely a black hole. Nearby, matter was heated until it emitted X-rays. Farther out, a broad envelope of gas absorbed energy and radiated blue light. Other streams of material may have been driven outward, continuing toward gas located even farther away. Yet every part of this picture was still based on signals arriving from a great distance. There was no image showing which star had supplied the material. No one knew for certain whether it had been torn apart during a single close encounter or had lived beside the black hole for a long time, gradually losing its outer layers. To answer that question, the story had to be carried back to a time before Whippet appeared in the sky. The powerful X-rays showed that the center was still active. The material surrounding it could not have appeared from nowhere within only a few days. It had to come from a process that began earlier, perhaps through many orbits, repeated episodes of gas loss, and a long period during which the entire system remained beyond human detection. Before the darkness around Whippet began to shine, a star and a dark object may have orbited one another for an immense span of time. With every silent revolution, the distance between them changed, bringing the star closer to the boundary beyond which it could no longer hold itself together. If a black hole truly lay at the center of Whippet, the story of the event did not begin on the night the point of light was discovered. It may have begun millions of years earlier, when the two objects first entered a slow dance together in the dark. If a black hole truly lay at the center of Whippet, the story did not begin on the night the point of light appeared on a screen at Palomar. It likely began much earlier, when two objects were still orbiting one another in a distant star system without producing any signal clear enough for humans to recognize. One was a large, hot, luminous star. The other was almost completely hidden in darkness. There was no true stillness between them, only gravity holding both objects in a dance that continued through countless orbits. Many stars in the universe do not live alone. They are born near one another from the same cloud of gas and continue moving around a shared center. Some pairs are nearly equal in size, while in others, one star is larger, hotter, and ages more quickly than its companion. Because it consumes its internal fuel at a faster rate, the more massive star usually reaches the end of its life first. After a long sequence of transformations, its remaining core may become an extremely compact object, perhaps even a black hole. From that point on, the system enters a new phase. The star that once shone more brightly has disappeared from visible light, but its gravity remains. The black hole continues orbiting the surviving star like an invisible companion. Unless nearby matter begins falling toward it, the black hole reveals almost nothing of its presence. The star's light overwhelms any faint signs, while the dark object continues moving in silence. For a very long time, such a system may look completely ordinary from a distance. Only one massive star appears within the host galaxy, while the dark object, traveling beside it, is absent from every image. The two continue orbiting their common center, each revolution resembling the one before it. The distance between them may remain wide enough for the star to retain most of its material, while the black hole captures only a small amount of gas drifting through space. That quiet appearance does not mean the system is truly motionless. The massive star continues changing from within. Heat and pressure hold its layers of gas against gravity, but the fuel in its core cannot last forever. As the star enters later stages of its life, its internal structure becomes more complex, while its outer layers become easier to push into space. Even without a nearby black hole, massive stars can produce powerful outflows during the final parts of their evolution. Gas leaving the star does not disappear the moment it escapes the surface. Some of it continues drifting outward, expanding into thin layers around the system. Other material passes through the black hole's gravitational reach and is pulled away from its original path. Streams of gas moving closer may spiral toward the dark object, heat up, and emit a faint amount of light. Yet, if the rate of mass loss remains too low, that signal may still be far too weak to stand out against the glow of the entire galaxy. Over time, the space around the two objects gradually fills with traces of the star. This is not a uniform shell or a motionless cloud. Material expelled at different times will move with different speeds, densities, and directions. Older gas travels farther away, while newer gas remains closer to the star. The system slowly becomes surrounded by overlapping regions of matter, like successive ripples spreading outward from the same point. Some models suggest that the star in the Whippet system may have been a Wolf-Rayet star. The name refers to a class of stars that are extremely massive, intensely hot, and have already lost a significant portion of their outer layers. They no longer resemble the Sun or many other familiar stars. Deeper parts of the star become exposed, while powerful winds continue carrying material into space. This is not a confirmed conclusion about Whippet, but it fits the idea that the star had been losing gas for a long time before the major event occurred. A star like this would not need to be destroyed immediately by the black hole. It could live beside the dark object through many orbits, losing a little more material with each passage. The black hole would capture some of the gas, while the rest spread outward around the system. From a great distance, this process might be too faint to produce a noticeable point of light, yet each lost layer of gas would quietly prepare the environment for what would happen later. The distance between the two objects would not necessarily remain unchanged forever. Each time gas left the star or moved from one object to the other, the motion of the entire system could shift slightly. Gravitational interactions unfolding over long periods might gradually tighten the orbit, or make it increasingly unstable. The change during a single revolution could be extremely small, but over thousands or millions of orbits, those effects could accumulate enough to bring the star ever closer to the black hole's intense gravitational field. There would be no clear moment announcing that the system had crossed into danger. From far away, the star would continue to shine. The black hole would remain almost invisible. The orbits would continue in darkness, only slightly faster or tighter than before. Yet with every close approach, the star's outer gas would feel a stronger influence. Some material would be pulled out of place. Streams of gas connecting the two objects would grow denser, and the black hole would begin receiving more matter. The increasing inflow of gas could make the region around the black hole brighter, though not necessarily bright enough yet to resemble Whippet. It would be like the build-up before a storm, when the wind has strengthened and the clouds have thickened, but the main event has not yet begun. What astronomers observed in 2024 may have been only the final moment of a process that had unfolded over an immense span of time, after the system had moved too far to return to its former state. The star was losing its outer layers, not only because it was growing old. The nearby black hole was also continually distorting its shape. The side of the star facing the dark object was pulled slightly more strongly than the far side. While the distance remained large, that difference was not enough to tear the star apart. It only distorted the surface slightly and made gas on the nearer side easier to lose. As the orbit tightened, the imbalance grew stronger, turning each revolution into a new test of the star's ability to hold itself together. Throughout this period, the lost layers of gas continued, moving outward. Some had left the system long before Whippet flared. By the time the main event occurred, they may already have traveled a great distance from the center. Other layers were expelled later and remained nearby. As a result, the space around the system was not empty, but more like a sea filled with many layers of matter, where the density varied from one region to another. This helps explain why the event did not end with the initial blue light. When newly ejected material was driven away from the central region, it needed time to cross the distance between the black hole and the older layers of gas. Only after many days or weeks would the fast-moving outflow collide with that surrounding material and produce radio signals. The early light told the story of the region near the center, while the later radio waves revealed collisions taking place farther away. In other words, what Whippet emitted during its first few months may have been shaped by a history that began much earlier. The outer gas observed around the event was not created entirely on the night of the flare. It was material the star had lost over many stages. When the new outflow rushed into it, the older gas became a background against which telescopes could measure the speed and energy of the ejected material. There was no way to go back and photograph the system before the event. The faint light from the star and black hole at that time had blended into the overall glow of the host galaxy. All astronomers could do was examine the structure of the present event and work backward into the past. A gas-rich environment suggested that the star had already been losing material. Weak hydrogen signatures could be consistent with a star that had shed most of its outer layers. Strong X-rays pointed to matter being heated near a compact object. Each detail added another piece to a history no one had witnessed directly. The binary system scenario was therefore compelling, not because it explained every signal with certainty, but because it connected many separate clues within a single story. A massive star lived beside a black hole. The star aged and lost gas. The black hole captured some of that material. The orbit gradually tightened. Layers of gas accumulated around the system. Eventually, the distance became so small that the former stable arrangement could no longer survive. Even so, many details remain unconfirmed. No one knows exactly how massive the original star was, how much material it lost, or the precise mass of the black hole. A Wolf-Rayet star is only one possibility proposed because it fits some of the observed features, not because such a star was directly imaged. The system may also have followed a different path, in which a massive star approached the black hole on its own orbit without spending a long time beside it. The available data allow plausible scenarios to be constructed, but they cannot turn the past into a clear recording. Every possibility must be treated with caution. What can be said with greater confidence is that the matter around Whippet did not appear from nothing. Before that region of sky flared, a massive star, an extremely compact object, and an environment filled with multiple layers of gas were already present together. Within that darkness, the two objects may have orbited one another through countless cycles. The star continued to shine, while the black hole revealed itself only through gravity. Each slow revolution carried them closer to a boundary neither could avoid. As more and more gas was pulled away from the star, the system gradually lost its ability to remain in balance. An event prepared over an immense span of time ultimately needed only a few days to reveal itself to the universe. This is why Whippet's flare was fast without being truly sudden. It was sudden only to telescopes on Earth. In that distant star system, everything had likely been changing little by little through many orbits. The brilliant light was merely the final sign of a process that had been unfolding quietly for a very long time. The star lost gas, the black hole received more material, and the distance between them continued to shrink. Older layers of matter drifted outward, forming the surrounding region through which later outflows would travel. Near the center of the system, the orbit grew tighter. The side of the star facing the black hole began to feel a stronger pull than the side farther away. Eventually, that difference no longer caused only a slight distortion of the star's surface. It began affecting the entire structure, pulling the nearer side forward while the far side lagged behind. The star entered a region where the gravity holding it together was no longer strong enough to resist the pull of the dark object beside it. After millions of years of existence, countless revolutions, and layer after layer of gas leaving its surface, the system finally reached its most fragile limit. The distance between the star and the black hole had now become too small. Gravity was no longer merely distorting the star, but beginning to draw it into long streams of matter around the dark region. From the moment the distance between the two objects became too small, the black hole's gravity no longer merely shifted the star's surface slightly with each orbit. The side facing the dark region was pulled more strongly, while the opposite side still tried to remain attached to the rest of the star. At first, this difference was very small, but it grew rapidly as the star moved deeper into the gravitational field. Layers of gas that had once moved together began to lose their uniform motion, and the nearly spherical shape maintained through most of the star's life was gradually stretched toward the black hole. On Earth, we can see a vastly gentler version of this effect in the tides. The moon does not pull on every part of Earth with exactly the same force. The side of the ocean facing the moon is slightly closer, and therefore feels a somewhat stronger pull, while the far side feels a weaker one. That small difference helps cause the seas to rise and fall in a regular rhythm. Earth is strong enough to preserve its overall shape, and the moon's pull is far too weak to cause anything more severe. Near a black hole, the same principle unfolds with such intensity that a star can no longer resist it. No direct collision is required. A black hole is not a solid wall that a star must strike before being destroyed. The orbit only needs to carry the star close enough for the difference in gravitational pull between its near and far sides to disrupt its internal balance. The side facing the black hole is drawn forward, while the more distant side falls behind. Between them, the star's material is stretched into an immense ribbon of hot gas. The star is still trying to hold itself together through its own gravity. Every layer of gas is pulled toward the center, just as it had been for millions of years. But that internal force is no longer strong enough to overcome the black hole's pull. The outer layers, already more weakly bound and previously stripped by stellar winds, begin separating more quickly. The first streams of gas leave the surface, extending along the orbit and becoming thinner and longer with every passing moment. From a distance, the process can be imagined as a drop of liquid being pulled in opposite directions. At first, it is only slightly distorted. Then its center grows thinner as the two ends are drawn farther apart. A star is not a liquid in the familiar sense, but most of its matter exists as extremely hot gas. When gravity changes sharply from one location to another, the entire body can be stretched into a shape it had never taken before. Astronomers call this kind of destruction a tidal disruption event. The term may sound complicated, but the underlying picture is simple. An object passes too close to a powerful source of gravity. Its nearer side is pulled more strongly than its farther side, and its structure can no longer remain intact. For Whippet, however, this term describes an important possibility, not a sequence that was directly observed like a recorded film. No telescope watched the star being stretched in real time. At a distance of more than 1 billion light-years, the entire region still appeared as a single unresolved point of light. Astronomers had to work backward from the energy released, the speed at which the light changed, the X-ray signal, and the traces that appeared later. From those fragments of information, they reconstructed an event that may have unfolded around the dark object at the center. As the outer gas was pulled away, the star did not necessarily vanish all at once. Its denser inner regions may have retained their structure for a time, even after the surrounding material had formed long streams. Some of those streams were drawn toward the black hole. Other portions gained additional motion as they were torn free and traveled in the opposite direction. Matter that had once belonged to a single unified star began following many different paths. The material thrown outward did not disappear from the story. It continued moving through the environment around the system, carrying heat and momentum from the moment of disruption. Later, when faster outflows from the central region caught up with it, new collisions would occur and produce radio signal. Yet the material most important to the initial light was the portion that remained gravitationally bound to the black hole. These streams did not fall straight toward the center. They still carried the orbital motion of the original star. So after being torn away, they continued sweeping around the dark region. Some followed longer paths, while others returned sooner. Instead of disappearing in a single moment, the material came back in separate waves, like many swells created by the same disturbance, but reaching the shore at different times. The first returning material may have produced Whippet's extremely rapid rise in brightness. Later streams continued supplying energy after the visible light had begun to decline. The uneven return of material may also help explain why the X-rays weakened and then brightened again around day 50. The central engine did not receive fuel at a constant rate. It was fed by ribbons of gas that had once belonged to the star, each one following a different orbit and returning at a different time. A star being torn apart during a single close encounter, however, is not the only explanation under consideration. The Whippet system may instead have entered the final stage of a long merger process. In that scenario, the star and black hole had already been orbiting one another along an increasingly tight path. The star continuously lost material, the orbit narrowed, and the two objects gradually moved together rather than having a distant star suddenly pass too close to the black hole. The difference between these two scenarios lies in the history before the event. One involves a close encounter followed by rapid destruction. The other is the ending of a binary system that became unstable over many orbits. Both could deliver a large amount of material close to a black hole within a short period. Both could also produce intense light, X-rays, and outflows driven into space. The current data are not sufficient to determine which path the system followed. Whippet's signals do not seem to fit any overly simple picture. The visible light rose and faded very quickly. The X-rays followed their own pattern of change. The radio waves arrived later and revealed collisions occurring at greater distances. One model may explain the blue color well but fail to reproduce the X-rays. Another may fit the dense gaseous environment, but struggle to explain the full speed of the rise. The event therefore remains an open question, with several possibilities still requiring further testing. What is more certain is the amount of matter that entered the region around the compact object. A source shining with the equivalent brightness of hundreds of billions of suns could not have arisen from a thin cloud of gas passing by chance. Whippet required a massive flow of material delivered into a powerful gravitational environment, where its energy could be released over a short period. A black hole fits that central role, even though the star's exact history has not yet been seen in full. Near the black hole, the stretched material did not retain a uniform temperature or density. Streams of gas collided, became compressed, and heated up. Some of the initial energy may have escaped as ultraviolet light and X-rays. Other energy was absorbed by the thick outer gas and re-emitted as blue light. What telescopes recorded, therefore, came not only from the moment the star was disrupted, but also from a series of collisions that followed. The event can be imagined as a river dividing into branches. At the beginning, all the material belonged to the same star. After passing through the intense gravitational field, one branch was thrown outward, another curved back toward the center, and some of the material may have remained attached to a surviving core. These streams met at different times and produced their own distinct signals. The observed light was the sum of that entire process, not a single flash released at the moment of disruption. It is also impossible to know whether the star was completely destroyed. Its denser core may have survived the first close encounter, continued orbiting the black hole, and lost more material during later passages. Another possibility is that the entire star was torn apart, but the streams of gas preserved their structure long enough to produce signals that emerged much later. When hydrogen and helium appeared after more than a month, they showed that the material was not expanding as a uniform sphere. Distinct regions of gas were still moving through the system in different directions. From the perspective of observers on Earth, the moment when the star lost its shape remained beyond direct view. No image captured half of the star being drawn toward the black hole, and no clear outline revealed the dark object at the center. There were only the consequences unfolding across different wavelengths. Blue light appeared first. X-rays revealed the deeper region, and then radio waves signaled that material had traveled outward and collided with older gas. The way these signals followed one another helped transform a single point of light into a story with a clear sequence. First, an immense amount of energy was released within a compact region. Then the central source remained active. Finally, the expelled material reached the outer environment. Each clue was consistent with a system in which a star had lost a large amount of matter beside a black hole. Whether the event was a rapid disruption or the final stage of a long merger, the decisive moment came when the star's material could no longer move as a single body. From then on, each part began following its own path. Some escaped the system, some remained gravitationally bound. The returning streams carried fuel back toward the center, extending Whippet's activity far beyond the first few days of its flare. The star, therefore, did not vanish the instant it was pulled out of shape. It continued to exist in other forms. In the gas traveling outward, in the ribbons of matter orbiting the black hole, in the blue light re-emitted by the broad surrounding envelope, and in the X-rays escaping from the hottest region. What had once been a single object had become the entire luminous environment around the darkness. The returning material carried an enormous amount of motion. It could not suddenly stop and fall straight into the black hole. Streams of gas swept past one another, curved around the center, and collided. With every encounter, they lost some of their motion, became compressed, and heated up. Each orbit carried the material deeper, while releasing more energy into space. This was where most of Whippet's light truly began to be produced, not at the instant the star was stretched apart, but as the returning fragments met, collided, and gradually formed a hot, swirling region around the black hole. The star had lost its original shape, but its material continued moving around the dark region. The streams drawn back toward the center did not fall directly into the black hole. They curved along orbital paths, collided with one another, and slowly formed a hot, luminous ring of matter around the center. The star had lost its original shape, but its material continued moving around the dark region. The streams of gas drawn back toward the center did not fall directly into the black hole. Instead, they curved along orbital paths, collided with one another, and gradually formed a hot, luminous ring of matter around the center. This was the stage that transformed what remained of the star into the immense energy source recorded by telescopes. The moment the star was stretched apart only marked the beginning of the event. The brightest light came later, when streams of gas that had once belonged to the same object began meeting again along different paths. Before it was disrupted, the star had already been moving around the black hole at tremendous speed. Every layer of matter within it carried that motion. When gravity tore the star into separate streams of gas, its previous movement did not disappear. The fragments continued rushing forward, much as an object thrown sideways follows a curved path instead of falling straight to the ground. The black hole's gravity pulled them inward, while their orbital motion carried them around the center. As a result, long ribbons of gas kept bending through space, sometimes moving farther away, and sometimes returning without immediately vanishing into the darkness. Each stream carried a slightly different speed and followed a slightly different path. Material pulled from the side nearest the black hole was affected differently from material on the far side. Some returned quickly, while other ribbons had to complete a much longer journey. When these streams met, they did not merge gently. They approached from different directions, collided, became compressed, and heated up. Part of their motion was converted into heat, ultraviolet light, and X-rays. After many such encounters, the material no longer followed the long, chaotic paths of the beginning, but gradually gathered into a broad, swirling region around the black hole. We might picture a fast-moving current circling a deep opening. The water does not disappear the moment it reaches the edge. It spins around, collides with other currents, and only gradually moves inward. Around a black hole, the same process unfolds in hot gas, at far greater speeds, and in an environment with no solid surface. The swirling region is not flat or steady like a perfect disk. New streams of matter continually return and crash into the gas already there, causing the entire structure to tremble and change over time. Although its true shape cannot be seen, the rapid rise in brightness shows that the material was releasing energy at a tremendous rate. The black hole at the center still produced no light of its own. This is easy to misunderstand when an event is described as a black hole awakening or flaring in space. The black hole itself does not become a brilliant star. The light comes from matter that is still outside it, in a region from which signals can still escape into the universe. As the gas moves closer to the center, it travels faster, is compressed into a smaller region, and collides more violently. Before some of the matter crosses the boundary beyond which it can never return, it may release an enormous amount of energy. The darkness is revealed only by the luminous material moving around it. The image is like the empty center of a storm. We cannot see the force drawing everything inward, but we recognize its presence in the clouds turning around it. In Whippet, those clouds were the remains of the former star. They became hot enough to shine in several different forms. Visible and ultraviolet light came mainly from the wider layers, while X-rays brought observers closer to the hottest region. Each signal offered a different view of the same process, gas falling deeper into the black hole's gravitational field and releasing energy along the way. That energy did not appear from nowhere. The deeper the material fell, the faster it moved. Its violent motion caused the gas streams to collide, become tightly compressed, and reach extremely high temperatures. Some of the energy remained in the motion itself, while the rest escaped as radiation. This process is far more efficient than burning matter in the familiar way we know on Earth. Even a fraction of a single star's mass brought close to a black hole can produce more light than countless ordinary stars combined. At its most powerful, Whippet was estimated to shine with the brightness of roughly 400 to 500 billion suns at once. That figure does not describe the size of the black hole, nor does it mean that hundreds of billions of stars exploded. It simply expresses how much light the source emitted during its peak. That immense brightness may have begun with the material of a single star. After the star was pulled apart and its gas was delivered into an environment of extreme gravity. Even a comparison such as 400 billion suns is difficult to imagine, because the sun itself is already an overwhelming source of light by the scale of human experience. The distance from the sun to Earth is about 150 million kilometers, yet its light is still powerful enough to outshine nearly every other star in the daytime sky. Whippet lay more than 1 billion light-years away. Its light had spread across an immense region of space before only a tiny fraction reached our telescopes. Yet even that remaining fraction was enough for the source to stand out within its host galaxy and allow astronomers to measure changes occurring over only a few hours. That brilliance could not last forever. The material returned in separate waves, and the amount of gas feeding the central region changed over time. The first stream may have been dense and powerful, creating the peak brightness within only a few days. Later streams may have been thinner or followed different paths, causing the total light to decline. Even so, the swirling region around the black hole continued receiving material, consistent with Whippet remaining hot for many weeks, and with the X-rays brightening again after they had weakened. The central engine did not behave like a light bulb being switched on and off. It was more like a fire receiving new fuel in uneven bursts. The light produced near the black hole did not travel outward without obstruction. Surrounding the swirling region was a broad envelope of gas formed from material the star had lost before and during the event. Energy from the center illuminated this gas, was absorbed, and then re-emitted in forms that could escape more easily. As a result, the luminous region visible to telescopes could be far larger than the place where the energy was originally generated. The true engine remained buried deep inside, while the surrounding gas acted almost like a broad curtain, illuminated from behind. The image of a lamp behind a curtain, which helped explain the changing X-rays, also fits here. But this time, the curtain does more than block the light. It absorbs energy, becomes hot, and begins to glow on its own. An observer outside does not see the small bulb at the center directly, but instead sees the entire fabric illuminated. Around Whippet, the X-ray producing region may have been relatively compact, while the blue and ultraviolet light came from a much broader area. This difference helps explain how the visible source could appear so large and brilliant, even though the black hole and the hottest material occupied only a small region at the center. The outer envelope of gas was not completely uniform. Some regions were denser and held energy for longer, while others were thinner and allowed X-rays to escape more easily. As the material continued to expand, the structure of the envelope changed. A region that had once concealed the center could become more transparent, revealing signals that had previously been trapped. The blue light also weakened as the area of heated gas gradually contracted. Whippet's decline therefore reflected not only a decreasing supply of fuel, but also the way energy traveled through multiple layers of matter before leaving the system. The luminous ring around the black hole was not a structure isolated from the rest of the event. New streams of gas continued to flow inward, while some of the material near the center was driven outward. Pressure within the hot region, turbulent motion, and the powerful forces surrounding the flow could send gas in more than one direction. While most of the material gradually moved deeper toward the black hole, some of it was accelerated and launched back into space. This may sound contradictory. A black hole has such powerful gravity that light cannot escape once it crosses a certain boundary. So how can nearby matter be driven outward? The answer lies in the gas's location. The expelled material had not yet crossed that boundary. It was still moving through the luminous region outside, where streams of matter collided, exchanged energy, and changed direction. Some portions lost energy and fell deeper, while others gained additional motion and escaped outward. We might imagine many marbles rushing into a vortex. After colliding, some slow down and move toward the center, while others are knocked outward at greater speed. Around a black hole, the gas is not made of separate solid objects, but streams of matter can exchange energy in a similar way. The central region can therefore receive infalling material, while also producing outflows that move in the opposite direction. The gas driven outward would become the next part of Whippet's story. It carried energy from the deepest region of the system, passed through the glowing envelope, and rushed into the space beyond. There, older layers of gas were already waiting, expelled by the star over a long period before the event. When the new, faster material met this older gas, a powerful shock front began to form. Blue light was no longer the only signal. Radio telescopes gradually revealed that the event was still spreading outward, even as the central region weakened. The luminous ring around the darkness was therefore not only the place where matter ended its journey, it was also a kind of crossroad. Some of the gas continued into the black hole, carrying the final traces of the former star. The rest moved away from the center, traveling back into space and carrying the event's energy toward layers of material much farther out. Whippet had shone with the brightness of hundreds of billions of suns because matter orbiting the black hole collided and heated up before moving deeper into the darkness. Yet the engine did not retain everything it received. Within the turbulent flow, some material was driven outward at a speed great enough to travel farther than Earth's circumference in a single second. When that outflow struck the older material already surrounding the system, a new wave began spreading through the darkness. The outflow leaving the luminous region around the black hole did not rush into completely empty space. Along its path were layers of gas expelled by the star long before the night Whippet flared. The new stream carried energy from the central region, crossed the system at tremendous speed, and eventually caught up with older material expanding more slowly ahead of it. When the two flows met, the next stage of the event began. It did not produce a brilliant blue point of light, like the one seen during the first few days. Instead, it spread quietly through space over many weeks, becoming clearly visible only through signals beyond the reach of the human eye. The region near the black hole did more than gather material. Turbulent streams of gas continually collided, exchanged energy, and changed direction. Most gradually lost some of their motion and moved deeper toward the center. But not everything followed that path. Some gas gained energy through these collisions, accelerated, and was launched back outward before crossing the boundary beyond which nothing could return. From the hottest part of the system, an extremely powerful wind emerged, carrying traces of what had just occurred beside the darkness. According to the model proposed for Whippet, this outflow traveled at about 15% the speed of light. In a single second, it could cover a distance greater than Earth's circumference. That is still far below the speed of light, but it exceeds every motion familiar from daily life and anything ever built by human hands. At such a velocity, the material quickly left the X-ray emitting region, passed through the glowing outer gas, and continued into the wider space surrounding the system. Even at that speed, the outflow still needed time to reach the layers of matter farther from the center. Light from near the black hole had already escaped the system, crossed space, and reached telescopes on Earth before the outer collision became clearly visible. This is why the radio signal did not peak at the same time as the blue light. It appeared later, after the material had traveled far enough to begin interacting with the older environment. The gas ahead was not created entirely on the night Whippet flared. It had formed while the star was still alive, as its outer layers were repeatedly blown away and spread through the system. Gas lost earlier had traveled farther out. Later episodes of mass loss remained closer to the center. Over time, multiple layers accumulated around the star, each with its own density, speed, and direction of motion. The space surrounding the system, therefore, already carried the record of a long history before the major event began. Each episode of gas leaving the star was like another ripple spreading outward after the surface of water had been disturbed again and again. Earlier layers expanded ahead, while later ones followed behind, creating an uneven environment from the inside out. When the new outflow from near the black hole arrived, it could not pass through the older gas without leaving an effect. The material in front was compressed, heated, and swept into the new motion. At the boundary between the two flows, a broad wave began to spread. It was somewhat like the wall of water rising ahead of a fast-moving boat, where the water in front is pushed together, forced outward, and left in a long wake behind. There was no water or boat in the Whippet system, but the fast gas compressed the material ahead in a similar way. A region of intense compression formed, and continued expanding as the outflow moved farther from the black hole. Astronomers call this region a shock wave. The name simply describes a place where matter changes abruptly under the influence of an extremely fast-moving flow. In Whippet, the shock continued traveling outward, even after the blue light near the center had weakened considerably. An event that began within a very compact region was now spreading across a much wider volume of space, drawing more and more layers of gas into its influence. The radiation produced by the shock was different from the light generated around the black hole. Its clearest signature appeared at radio wavelengths, which human eyes cannot detect, but specialized telescopes can record. The deeper details of how individual charged particles create that signal are not necessary to follow the story. What matters is what the radio emission reveals. Material is moving rapidly, colliding with its surroundings, and continuing to carry energy away from the center. Each kind of signal, therefore, brings observers to a different region of Whippet. The blue light came mainly from the broad envelope of gas, heated around the primary energy source. X-rays originated closer to the place where matter was moving more violently, near the compact object at the center. Radio waves appeared farther out, where the outflow had left the inner system and struck layers of material the star had shed earlier. The three signals did not describe the same moment. Together, they traced a journey from the deepest region outward. When Whippet was observed only in visible light, the event seemed to be ending quickly. The point of light faded after reaching its peak, and each new image showed it growing dimmer. Radio observatories, however, recorded the opposite trend farther from the center. While the outer glow was declining, the shock wave was still growing. The outflow continued driving forward, expanding the reach of the event day by day. The delay between the blue light and the radio signal carried important information. The initial luminous region lay fairly close to the center, so its radiation left the system early. The radio emission became clear only after the material reached the older gas. That waiting period reflected the real journey of the outflow through the space surrounding the black hole. It was somewhat like lightning appearing before thunder, with two signals arriving at different times, even though they came from the same event. Here, however, the delay was not caused by sound traveling more slowly than light. It occurred because the matter itself needed time to cross the distance between the central region and the outer environment. The radio signal rising after the blue light had already passed its peak showed that the outflow was not moving into a vacuum. Enough material lay in its path to create a powerful collision. Changes in the strength of the signal over time also revealed that the gas surrounding the system was not distributed evenly. Denser regions caused the shock to grow stronger. In thinner regions, the outflow moved through more easily, and the signal shifted into a different rhythm. Each layer of gas was like an old page in the star's history. The most distant material may have left its surface long ago. The layers closer in reflected later episodes of mass loss, when the star and black hole had moved nearer to one another. The new outflow passed through these layers one by one, awakening traces that had drifted silently for a very long time. The radio waves therefore revealed more than the material recently launched from the central region. They also showed how the star had changed before it was pulled out of shape. A flare occurring in an almost empty environment would have evolved differently. Whippet, however, was surrounded by a dense, layered region of gas with a history of its own. That evidence fits the picture of a massive star that had been losing material throughout the final stages of its life, or of a binary system that had exchanged gas over many orbits. The brightest phase lasted only a few days, but the environment through which the shock was traveling had formed much earlier. The expelled material was also unlikely to form a perfect spherical shell. Near the black hole, gas may have escaped more strongly in certain directions. The older material around the system would not have been distributed evenly either, because it had been released by a rotating star that was losing gas while being influenced by its companion. When these two uneven structures met, the shock expanded more quickly in some directions and more slowly in others. The immense distance prevented telescopes from resolving its true shape, but the changing signal suggested that the event was not expanding uniformly like a simple sphere. By this point, the picture of Whippet had developed many layers. At the very center was a compact object, hidden in darkness. Around it, hot streams of gas swirled and emitted X-rays. A broader envelope absorbed energy and re-emitted it as blue light. Farther out lay material that had previously escaped from the star. The new outflow connected all these regions by carrying energy from the center toward the edge of the system. The shock front continued expanding for many weeks. Behind it was gas that had just been compressed and heated. Ahead of it lay an environment not yet disturbed. With each passing day, that boundary traveled farther, drawing once quiet regions into the event. The point of light in optical images had faded, but the space surrounding the system had not yet returned to its former state. A weakening source of light does not mean that the entire event has ended. It only means that less energy is escaping in one particular form. Accelerated matter still retains its motion. In space, where there is almost no friction, an outflow cannot stop suddenly. It continues until it meets an environment dense enough to slow it, compress it, or force it to transfer energy into other material. Whippet therefore continued to exist through motion, even after its brightest phase had passed. Energy once concentrated around the black hole was now being carried outward and spread across an increasingly wide region. The central engine may have been weakening, but the shock wave continued preserving traces of its most powerful stage, passing its influence into layers of gas beyond the original luminous region. For astronomers, each kind of signal became a marker along the timeline. The blue light recorded the period when gas near the center was heated intensely. The X-rays showed that matter remained active around the compact object, After the initial flare, the radio waves confirmed that some of the energy had left the center, entered the older environment, and created new collisions. When all three were placed together, Whippet no longer appeared as a solitary flash, but as a process spreading gradually from the inside outward. The outflow did not need to be seen directly for astronomers to know it had passed through. Radio waves preserved the traces of expanding matter as it transferred energy into its surroundings. Ripples on a pond reveal that something has fallen into the water even after it has disappeared from view. In much the same way, the radio signal showed that motion was continuing after the original source of light had nearly vanished. While the shock kept moving outward, the region near the center continued to change as well. The gas that had once concealed the energy source expanded and became less dense, allowing signals previously overwhelmed by the intense light to emerge. The nearly smooth spectrum of the early phase was no longer completely empty. After several weeks, faint features appeared at positions associated with hydrogen and helium. Their delayed appearance was connected to the thinning of the outer gas. Light from deeper regions could now escape more easily. Some distinct streams of material also became strongly illuminated enough to leave clearer signatures. Whippet was slowly revealing the part of the story that its overwhelming early brightness had hidden. The radio waves had carried observers far from the center, to the place where the new outflow met the older material. The chemical signatures that appeared later drew attention back toward gas lying deeper within the system. They were not as brilliant as the original peak, but they carried information that blue light alone could not provide. What material was still present, how it was moving, and whether everything was truly expanding in the same direction. Whippet did not end when the point of light began to fade. Part of the event was still rushing outward as a shockwave, while layers of gas closer to the center gradually exposed signatures that had once been hidden. After more than a month, hydrogen and helium finally appeared in the light. Those features did not gather into a single simple line. They separated into several components, showing that distinct streams of gas were still following different paths through the system. The new features did not gather into a single simple line. Instead, they split into several components, showing that distinct streams of gas were still following different paths through the system. During the first few weeks, Whippet's light was almost too smooth and too bright to reveal what kinds of matter were present within it. Only after the source had weakened considerably, the surrounding gas had become thinner, and light from deeper regions had begun finding a way out, did a few faint signatures finally emerge. About 20 days after the first light appeared, the Hubble Space Telescope observed Whippet in ultraviolet wavelengths. At that point, the source was still hotter than 20,000 degrees. Yet its spectrum showed almost none of the clear features normally associated with gas expelled from a star. There were no prominent lines indicating an expanding stellar wind, and few elements left easily recognizable fingerprints. Whippet resembled a page glowing so brightly that the writing across it had nearly been washed away. That emptiness persisted through most of the first month. Hydrogen and helium were certainly not unfamiliar materials within a massive star, but they had not yet appeared clearly in the light. The extreme temperature and intense radiation from the center may have driven the gas into a state in which its familiar signatures became very weak. The streams of material were also moving rapidly, causing light from many regions to blend together before reaching the telescope. Around 35 days after the initial discovery, the picture began to change. Weak signals associated with hydrogen and helium finally appeared in the visible spectrum. More notably, these were almost the only two elements to leave clear signatures at that stage. Other elements still did not emerge prominently. These traces were not as powerful as the blue light that had once covered the entire event, nor as intense as the X-rays coming from the central region. They were only small marks within the spectrum, easy to overlook had Whippet not been followed continuously for many weeks. Yet their late appearance carried a kind of information that the overwhelming brightness of the first few days could not provide. Each element interacts with light in its own way. Hydrogen leaves signatures at familiar positions, while helium leaves them at others. They are like delicate fingerprints, allowing astronomers to identify the matter that is glowing without ever approaching it to collect a sample. The light had crossed more than 1 billion years of space, yet it still preserved part of the story of the gas in which it was created. Hydrogen and helium did more than simply appear. Each signature also split into 2 branches. The separation between them corresponded to motion of thousands of kilometers per second. Put simply, one portion of the gas was moving differently from the rest, as though 2 streams of matter were glowing at the same time while following separate paths. Each branch remained relatively narrow rather than spreading into a completely chaotic smear. This suggested that the gas had not merely been thrown outward at random within a uniformly expanding cloud. Some portions of the material appeared to remain concentrated in fairly dense structures, surviving long enough to preserve their own distinct motion. The research team therefore described these features as evidence of dense, relatively stable regions of gas within an environment undergoing violent change. If the entire star had been disrupted into a symmetrical sphere of gas, the light would more likely have revealed a layer of matter expanding with relative uniformity. Whippet instead showed a clearer division. Within the unresolved region, there still seemed to be separate gas streams, elongated ribbons of material, or areas denser than their surroundings. Each region received energy from the center in a different way and left its own signature in the light. This was also the point at which the fate of the star became more difficult to determine. Some material pulled away during its close approach to the black hole may have survived as long streams. Those streams could continue orbiting the center, passing through different regions and becoming clearly luminous only when their viewing angle or energy input changed. The 2 branches of hydrogen and helium could then come from 2 portions of the same material, one moving in one direction, while the other followed another. Streams like these would not necessarily disperse immediately after being torn from the star. In the near-frictionless environment of space, they could remain elongated and continue moving around the black hole for a considerable time. The relatively narrow width of each feature suggested that the gas still preserved some structure rather than having fully blended into the hot flow around the center. This was one reason the idea of stellar material stretched into streams was taken seriously. Another possibility left open the chance that the star had not been completely destroyed. Its outer layers may have been stripped away while the denser core remained intact and continued orbiting the black hole. Each time the surviving remnant passed near the center, it could lose more gas and create new streams of material. In that case, Whippet would not be the result of a single disruption alone, but an event extended through repeated episodes of stripping. The current data do not directly reveal a surviving stellar core. No telescope can resolve a small object orbiting the black hole at such a distance. The idea arises only from the late-time signatures, suggesting that the gas remained concentrated in distinct structures instead of fully dissolving into the expanding material. There is still a great distance between an explanation that fits the data and a conclusion that has been proven. The story also allows for another possibility. The original system may have contained more than one star and a black hole. A third object could still have remained nearby, continuing to orbit the center after the event. X-rays and powerful outflows from the black hole region may have illuminated the surface of this star and stripped some of its outer gas into space. In that model, the late hydrogen and helium signatures could come from material being removed from a surviving companion star. This was one of the 2 main explanations proposed by the research team, alongside streams of matter torn from the disrupted star. That possibility would make Whippet's history far more complex. Instead of a simple pair of objects, the system may once have been a small group of stars whose orbits interacted over a long period. One star was destroyed, the black hole captured material, and another member remained within the region affected by the event. The 2 branches of hydrogen and helium would not necessarily belong to the vanished star, but could instead come from gas newly stripped from a star that was still alive. No explanation is currently strong enough to eliminate all the others. The hydrogen and helium features confirm the presence of gas and show that it was not moving as a uniform layer. They do not yet reveal the exact origin of each stream. Material remaining from the disrupted star, gas lost by a surviving core, or matter blown from a companion star could all produce similar appearances when viewed from such an immense distance. The greatest limitation lies in how Whippet appears through a telescope. The entire system remains only a single point of light. No image shows exactly where the two gas streams lie, how long they are, or in which directions they are tilted. Astronomers can only collect the light, separate it into its different components, and measure how it changes over time. The true shape of the system must be reconstructed from indirect clues. The work is much like listening to sounds through a thick wall. A footstep tells us that something is moving. Two different rhythms suggest movement in more than one direction. But sound cannot reveal how large the room is, where the objects are placed, or exactly who is inside. With Whippet, light played the role of those sounds passing through a wall more than 1 billion light-years thick. In this case, science does not arrive at an answer in a single step. Each observation only narrows the number of possible stories. The persistent blue color made a simple cloud of gas cooling rapidly increasingly difficult to explain. The return of the X-rays showed that the central region remained active after many weeks. The radio signal confirmed that material had been launched outward and was colliding with older gas. The late appearance of hydrogen and helium added another layer of complexity. Some of the material was still preserving its own structure and motion. When all these clues are placed together, Whippet no longer resembles an explosion expanding evenly and fading into space. It contains an active center, a broad envelope of luminous gas, outflows moving away from the system, an older surrounding environment, and smaller structures still traveling through the deeper regions. Each part became visible at a different time, making the entire event seem like a room illuminated from several angles, one after another. The late signatures also changed the way astronomers viewed the question of whether the star had truly disappeared. Its original form was certainly no longer intact. A large amount of matter had been pulled away, heated, and delivered into the region around the black hole. Yet losing its former shape did not mean that every part of the star had fallen into darkness. Its gas still existed in the central flow, in the material launched outward, and perhaps in a dense structure that had not been completely destroyed. Even if the star had been fully dismantled, its matter continued telling the story through light. The hydrogen and helium were remnants of an object that had preserved its own shape for millions of years. After the event, those layers of gas followed different paths, sweeping around the black hole, traveling outward, or remaining gathered in denser streams within the turbulent environment. As the source continued to fade, these signatures would weaken as well. The gas expanded, its density fell, and the central energy source could no longer illuminate every region with the same intensity. The streams of matter moved farther apart, making their information increasingly difficult to collect. The period during which hydrogen and helium appeared clearly was therefore only a brief window, opening after the brightest light had passed but before the entire system became too faint. Whippet seemed to offer humanity only a short time to see each part of it. The rise in brightness lasted only a few days. The X-rays changed over many weeks. Radio waves appeared after the outflow had traveled farther. Chemical signatures emerged only when the outer gas began to grow more transparent. Each window opened at a different moment and then closed again before the picture could become complete. This is why data from many telescopes and many different times had to be combined. One instrument recorded the blue light. Another followed the X-rays. Radio observatories detected the shock front far from the center. Later, optical observations found hydrogen and helium. No single set of data could explain Whippet on its own. But when placed in the proper sequence, they revealed a system far more complex than a single stellar explosion. At the deepest level was an extremely compact object drawing in matter. Nearby, hot gas produced X-rays, A broader outer layer emitted blue light. Farther out, the shock wave moved through older material. Between these regions, streams of gas had still not fully blended together, leaving two separate branches in the spectrum. The original star had lost its shape, but its matter had not become a uniform haze. What remained missing was a direct view of the origin of each gas stream. No one knew for certain whether the core had survived. The system may have contained another object, but the evidence was not yet clear enough to confirm it. The star may also have been completely destroyed, with the observed structures simply being streams of matter that preserved their form longer than expected. That uncertainty did not make the observations any less valuable. The data were strong enough to rule out some overly simple pictures, but not strong enough to force the entire story into a single explanation. Whippet preserved its most important mystery, even as its light nearly disappeared. After several months, the point of light that had once outshone hundreds of billions of suns gradually blended back into the faint glow of its host galaxy. The X-rays weakened, the radio emission continued spreading outward, and hydrogen and helium remained only as small features in the late-time data. The violent activity that had once surrounded the black hole began to slip beyond observation. The return of darkness did not erase what had been recorded. The sequence of light still preserved traces of the star, the returning gas, the hot central region, and the layers of matter thrown into space. From those records, astronomers could continue searching for an explanation even after the source was no longer clearly visible in the sky. By the time the final signatures appeared, Whippet had nearly completed the part of its journey that could be followed in visible light. The question was no longer only about what had vanished into the darkness, but also about the material that continued to exist after the event. The star may no longer have been whole, yet within the fading light, some parts of it still did not seem ready to leave the story. The star may no longer have been whole, but within the fading light, some parts of it still did not seem ready to leave the story. Streams of gas continued moving around the dark region. The shock wave kept spreading outward, and the signatures of hydrogen and helium appeared only briefly before becoming too faint. Whippet was approaching the end of its observable journey, not through a sudden moment of darkness, but through the gradual weakening of each kind of signal. Over many months, the point of light that had once stood out near the edge of the galaxy slowly blended back into the surrounding glow. In the earliest images, Whippet had overwhelmed much of the light at that location. Later, the host galaxy once again became the dominant feature, while the source remained only as an extremely faint point, difficult to separate from the stars and dim gas behind it. The same region of sky and the same galaxy were still there, but the immense change that had taken place was now almost invisible in ordinary light. There was no precise boundary marking the moment Whippet ended. The blue light gradually declined. The X-rays weakened according to their own rhythm. Radio waves continued to be detected as the shock front moved farther from the center. Each signal faded from view at a different time, like sounds in a room growing quieter one by one after the door has closed. The last sound to remain does not necessarily come from where the event began, but from more distant regions still responding to energy they received earlier. What remained in the data was not a clear image of the black hole, the star, or the stretched streams of matter. It was a sequence of changes recorded over time. A point of light suddenly appeared. Within only a few days, it rose to maximum brightness. The source remained blue longer than expected, showing that its temperature stayed extremely high even as its brightness fell. X-rays from deep inside weakened and then returned. Material driven away from the center continued into older gas, producing radio emission that appeared later. Finally, hydrogen and helium left signatures divided into several components within the fading light. Each individual observation told only a short part of the story. Only when arranged in the correct order did they form a more complete journey. Whippet did not flare and vanish in a single step. Energy began within a compact region near the center, spread through the gas emitting blue light, drove some material outward, and continued affecting the environment around the system. The story moved from the inside outward, while gradually unfolding from the brightest signals to the weaker traces that appeared last. Some conclusions can be drawn with greater confidence than others. The source required an extraordinarily powerful central engine that remained active even after the visible light had reached its peak. The persistent blue color did not fit the picture of gas receiving energy only at the beginning and then cooling on its own. The X-rays showed that matter was still being heated within a smaller, more violent region. The radio waves confirmed that a fast outflow had left the center, while the outer environment already contained multiple layers of older material. These features are consistent with a large amount of gas falling rapidly toward an extremely compact object. Among the available explanations, a black hole is the leading candidate. Its gravity could pull material away from a star, accelerate the returning gas streams, and create an environment hot enough to produce X-rays. The flow of matter around the black hole could also explain the immense energy that made Whippet shine with the brightness of hundreds of billions of suns at its peak. Even so, consistent with is not the same as seen directly. The black hole did not appear in an image as a dark sphere with a clearly defined edge. Telescopes recorded only what the surrounding matter did under its influence. The gas heated up, moved faster, emitted light, and was driven outward. From those effects, astronomers inferred the presence of the hidden object at the center. The star's past also cannot yet be reduced to a single explanation. It may have passed too close to the black hole and been stretched into streams of matter during one dangerous encounter. Another possibility is that it had long existed in a binary system, with the black hole gradually losing its outer layers before finally merging with the dark object after many orbits. Both paths could deliver a large amount of gas close to the center within a short time while also producing powerful outflows. The data do not reveal whether the star was completely destroyed. The late hydrogen and helium signatures may have come from streams of matter that preserved their structure after being pulled from its surface. They could also be related to a surviving core, or even to another star still present in the system. At this point, no explanation is strong enough to eliminate all the others. The black hole's exact mass has not been measured directly either. Models can provide ranges of values that fit the observations, but Whippet is too distant for the orbits of individual objects to be resolved. Changing the assumptions about the star's structure, the amount of returning gas, or the way the surrounding material absorbed light could alter the estimate. The story should therefore not end with a number more certain than the data truly allow. Even the broader class of events to which Whippet belongs still contains many unanswered questions. Fast, blue, extremely luminous sources appear to share certain features, but this does not prove that they are all produced in the same way. Some may begin with the collapse of massive stars. Others may involve black holes and stellar companions. Whippet could be an extreme member of a known group, or it could represent a rare branch that humanity has encountered only a few times. The event's greatest value does not lie in giving science one final answer. Whippet shows how an almost invisible black hole can be discovered through the changes occurring around it. The dark object may exist for a very long time without producing any noticeable signal. Only when a star comes close enough and matter begins leaving its surface does the region around the black hole begin to shine. For most of its existence, an isolated black hole does not resemble the violent image often found in the imagination. It does not continuously consume everything around it, nor does it emit light to reveal its location. A star can orbit it stably as long as the distance remains large enough. The transformation begins when the orbit tightens, the outer gas is pulled away, and matter moves deeper into the gravitational field. Whippet captured precisely that rare stage. The invisible dark region became surrounded by a ring of hot gas. Energy from the center illuminated a broader envelope, causing the entire system to glow in blue and ultraviolet light. Some gas moved deeper inward, while other material was driven outward. For a few brief days, a place that had once been almost anonymous became one of the most powerful sources of light in the distant sky. As the source faded, the black hole did not disappear. It simply returned to a state closer to the one it had occupied before the event. The amount of surrounding material declined, the gas became thinner, and the light strong enough to reach Earth gradually weakened. The dark region once again sank into the background of its host galaxy, difficult to distinguish from billions of other stars. Events like Whippet are especially difficult to detect because their brightest phase is so brief. A telescope that overlooks that region of sky for only a few nights may see the source only after it has already begun to fade. If the interval between observations is too long, the entire rise in brightness can disappear from the data. This is why programs that repeatedly photograph the sky at high frequency are so important. They do more than create beautiful images. They capture changes that unfold faster than traditional observing schedules can follow. In the future, as more telescopes continuously monitor wide regions of the sky, the number of similar events may grow. Each new discovery will help astronomers determine just how rare Whippet truly is, which features are genuinely common, and whether all sources in this class share the same history. A single case always leaves many possibilities open. A larger group will gradually begin to reveal the underlying patterns. Whippet also demonstrates the value of observing the same event through many different kinds of signals. Visible light alone was not enough. Radio waves traced the material that had traveled farther outward. The late signatures of hydrogen and helium added information about the composition and motion of the gas. No single telescope held the entire story. The collaboration was much like reconstructing an event through several witnesses standing in different places. Someone nearby sees only the opening moment. Another person farther away notices the wave passing later. Each tells a different part of the story, and their accounts may not seem completely alike. Only when those accounts are placed together does the sequence of events gradually become clear. The data continue to exist even after Whippet's light has nearly disappeared. Images, color measurements, X-ray signals, radio waves, and spectral features are preserved so that many research teams can examine them. A new model may be proposed years from now, when analytical methods improve, or when another similar event appears for comparison. In that sense, the scientific story of Whippet did not end when the point of light faded from the sky. The light itself had traveled for far longer than humans spent observing it. More than 1 billion years ago, in a distant galaxy, a star may have entered its final stage beside a black hole. Matter left its surface, the orbit changed, and the region around the dark object began receiving more gas. The event unfolded, light was released, and then began its journey across space. When that signal left the galaxy, there were no humans on Earth. The continents occupied different positions. Life was still changing across immense spans of time. Countless species appeared and disappeared, while each photon from Whippet traveled silently toward a region of space where the solar system would eventually develop the conditions for a civilization capable of watching the sky. For hundreds of millions of years, the light crossed the space between galaxies. It did not know whether anyone was waiting ahead. Most of the signal continued outward in other directions and would never reach Earth. Only a tiny fraction followed the right path and eventually fell upon the mirror of a telescope at Palomar. When the point of light was recorded in 2024, the actual event had already receded deep into the past. The star may have vanished long ago. The expelled gas had traveled far from the black hole. The shock wave had altered the environment around the system. What humanity called a new event was new only to observers on Earth. That moment connected two eras separated by more than 1 billion years. At one end was a star approaching the darkness and releasing its energy. At the other were astronomers looking at a screen and noticing a point of light that had not appeared in the previous image. Between them was only light, traveling through space long enough for an entirely different world to arise before it finally arrived. AT2024WPP did not give us a clear image of the vanished star, nor did it reveal the true shape of the black hole at the center. What reached Earth was a brief sequence of signals: blue light flaring and fading, X-rays disappearing and returning, radio waves continuing to spread after the central region had dimmed, and traces of hydrogen and helium emerging when most of the event had nearly passed. From that sequence, a distant story gradually took shape. A massive star may have lived beside a black hole for a very long time. The distance between them narrowed over countless orbits. Matter was pulled from the star, curved around the dark region, collided, and heated up. For a few days, the ring of gas around the black hole shone with the brightness of hundreds of billions of suns. Then the source began to weaken. The gas expanded, streams of material traveled farther away, and the black hole gradually returned to an almost invisible state. The host galaxy once again appeared only as a faint patch of light in the images, much as it had before Whippet emerged. The darkness closed again, not because the event had never happened, but because the energy source was no longer powerful enough to remain visible across the immense distance to Earth. Whatever remains is still moving out there, only too faint and too far away to be seen clearly. For a brief time, the darkness around the black hole shone brightly enough to send a signal across more than 1 billion years of space. By the time that light arrived, the world that received it had not even existed when the journey began. Whippet has now almost disappeared from the sky. But within the data it left behind, the moment a star came too close to the darkness is still preserved, waiting for humanity to continue reading its final traces.